Hello everyone, this is Mixer Samuel, software engineering student at Makerere University in Uganda. In our previous episodes, I've been looking at a music generative model, artificial intelligence model, and this model is a large neuroacoustic model for frequency-guided music therapy. And the keywords we have large acoustic generative models, music therapy, neuroacoustics, therapeutic music frequency mapping, generative AI for health, and personalized soundscapes. So I'm going to talk about the few final touches of this project, and this video marks almost one of the last episodes to the development of this model. So in today's presentation, we are going to talk about the introduction, related work, problem statement, research questions and objectives, research contributions, methodology, architecture, and mathematical foundations of each model I've looked at, dataset description, results, limitations, conclusions, and then future works. So let's start with the background and introduction, where I'm going to talk about the keywords we looked at on the first slide. We have large acoustic generative models, and this refers to AI models designed to generate speech. As you can see, the word acoustic, which means something like music, and generative, generation, and then sound, which covers the large acoustic generative models. Then we look at music therapy, and this is a form of therapy obtained from music to promote emotional support, expression, relaxation, and healing. Then you have neuroacoustics, and this refers to how the brain processes sound. And we have therapeutical frequency mapping. This involves specifying the sound frequencies which will promote healing or relaxation of the brain at different targets. And then you have generative AI for health, refers to AI or generated to cater in, for anything in the medical research or field. Then we have personalized soundscapes. These are just audio tailored to individual specific needs or preferences. And we have related works, uh, the papers we read, and also the works of other people we looked at. And these papers were many. We looked at 6 papers, and because I don't have a lot of time, I'm going to just talk about a few. First, we have the effects of music and auditory beat stimulation on anxiety. At this paper, we looked at it, and then we came up with the results, the architecture limitations, and then the context limitations. So we tried to look at different papers to see what they didn't cover, and then we'll cover in our music system or AI system. Yeah, I can't go through all these papers one by one, but if at all you can, pause and then you look through these different papers. You can learn a few things and also know the limitations which are in those papers, which we looked at and tried to rectify in our system. They have the domain application problem, the problem we're trying to solve. And the major problem we're trying to solve is the inability to create prescriptions by the therapists tailored to one individual. Remember, when you go to a therapist, you have to tell someone your problems which you're facing, then they can guide you. But this can also be done using music. And as we have looked at those different papers, those papers or previous innovations, were not covering most of these things. So now that's the problem we're trying to solve, because someone can be there and they want to maybe listen to something which can make them feel better, not just to talk to someone, but also listen to something. And also during a therapy session, this music can be played in the background, which can also contribute to the healing of that person. Then the computation problem, the main challenge is to extract meaningful features from audio signals and then generate therapeutic music, because in this case we have to get music, generate features from that music, map it with the clinical findings or targets we found, and then try to generate new music. Try to generate new music from what we have. And this is done through feature extraction, whereby the system identifies sounds linked to those therapeutic conditions. We use AI models to create adaptive soundscapes for each user's needs, because now we look at each person's needs. And the goal is to make the model to understand or create sounds scientifically and therapeutically proven to heal or cater for the neurological and psychological conditions. Okay. And research questions and objectives. The objectives are trying to convert audio files into spectrograms, and this is done in order to reduce the computation time. And because we are trying to look at music, and music is not easily, like, you can't look at it with just when it's playing. You have to first convert it to maybe something which is simpler, which you can work with. And in this case, for us, we try to put it into spectrograms. And we combine, because now the music we add or we got were just 4 seconds audio files, and then we had to try to combine those multiple short audio clips into something which is large, because no one is going to be listening to just 4 seconds. And then we try to map audio files to certain psychological states. Such questions we looked at, because before we started to develop this system, we had to first look for the data set. So we're like, where can we get the data sets that have the data we require? And how can we relate the music to the psychological states? And that's why we read the different papers in order to come up with solutions. And then research contributions and outputs. So outputs are converted the audio files to spectrograms, converting information from papers into knowledge graphs, then mapping the musical frequencies to their effects on the brain. Now, on system architecture, how the system is going to be functioning in the user's perspective, and also the back, what's taking place behind the scenes. The user inputs a condition, then you have the BAT model, which maps the keywords to the music parameters. The model will map those conditions to the different music which is needed, and then we generate an audio file. I'm going to be fast because time is really, because I want to make this a 15-minute video, so I'm going to be fast. And then the models we use the models we trained, because I wanted to train many models and then come up with the best one. We looked at the music gen, which uses transformers, and in this case we convert the continuous audio waveform into different tokens through the residual vector quantization. And this is the mathematical formula for that. Then with condition, we map the user prompt into a fixed numerical vector, because working, we have to first convert the prompt. In this case, we preset like the different targets, that if at all someone puts I lack sleep, that's a sleep disorder. So we return that into a fixed numerical vector. And then generation predict in for the music gen, because it uses transformers, it predicts the next audio token using the autoregressive transformer decoder. And this it uses the attention model. So that's the formula. And then the output, we have to convert the generated tokens into audio waveform. Yeah, so that's the music gen. And for it, one of its advantages, it trains faster. Because just we convert tokens, it trains faster. and also because it uses the transformer, it decodes. So it works well with temporal coherency, because now in this case we have 4 seconds audios, and then at a certain time we have to concatenate to make like a 10 minute audio. And here is the architecture of that model. And then we have the large acoustic generative model. This just framed it that way, but that's not like the its name. That's not a standard name, and this bases on VAE, which is a variational autoencoder, whereby it encodes the the audio in two latent spaces, and then afterwards it then decodes. So is the mathematical formula for that. And one of the limitations, we found that this may blur details in reconstruction of the audio, because it has to encode and then decode after. And then training requires careful tuning of the latent dimensions, and this can underfit or overfit if the latent space is not well regularized. Yeah, and then we have the other one, the last one we train. This is a wave gun, which uses guns, which are generative adversary networks. And this uses the generator to distinguish between the real and then the fake waveforms, producing realistic waveforms without spectrogram invasion. So this is like, after training, it will see that it's clusters, that when you put it will use the discriminator to distinguish between the real versus the fake. Then the generator will try to create fake samples. We try to create fake samples. And then we have real data. In this formula, this P data stands for real data distribution. Right. Then out of those models, we use different matrix to select which one is best. And this case, the testing and then the validation, we looked at the R squared score, RMS, temporal currency, because I'm dealing with music, and at a certain point you have to combine those different spectrograms or audio files to make a big audio. And then accuracy, because we want to see, because this is a medical, something which is medical, so accuracy is key. And testing, these are the outcomes, and then validations, these are the outcomes for the different models we trained. Yeah, and then for the dataset we use the NCF dataset, and this is the link to that dataset. I think I'll put it under the description, where we add audio files and then their features. In the audio files, we extracted features like MFCC, spectral, centroid, spectral, chroma, zero crossing rate, and then for the the clinical targets, which are targeting on the brain, we have anxiety reduction, dopamine boost, serotonin boost, and so on. So we had to observe the different patterns between the instruments. And for the samples we used, because this data set is 300,000 plus samples, and during training, since we didn't have a lot of hardware resources, so we just picked a sample of 100,000 data points, whereby we use the training set to be 70% and the testing to be 15%, the validation 15%, and these are the numbers. So the classes we have on this data set, music is like clustered into different classes. Those audio files are clustered into different classes, whereby we have the acoustic and electronic, synthetic, and these are the numbers. So I tried to visualize the waveform and the spectrograms of those different classes, and they are here. For acoustic, it's like for electronic, it's like that. For acoustic and then synthetic, it's like that. And then visualizing the different features. So I'm trying here to show the features in those music because each audio file add features, and those here are the features visualized for bass, keyboard, guitar, the instrument family. And then therapeutical potential heat map, because after mapping the different therapeutical targets to the different uh, to to those audio files. So I try to create a heat map to see whether we're tampering or working with or the therapeutical targets are being catered for. And then model selection, we selected the music gen because for it had a good accuracy and then topical coherency, better than the LGM and then the wavegun. And for it trained faster, so it takes a little time to train than the others. And I think I talked about the differences, the other differences between the others and the limitations. So now the result, I tried to visualize the correlation between musical features and then the therapeutical effects and then the attention patterns because we're using a transformer model. So I tried to visualize the attention patterns for the therapeutical music generation. Then demonstration of the developed product, because now we have the product. The system just or constantly monitors the use and then generates music that serves as a tool for music therapy. Input, we gather real-time biometric data which indicates the current mode of the patient. Processing, the model applies pre-mapped neuroacoustics and creates a unique song. Music is played for the patient and then therapeutic effects are observed. Okay, limitations. We faced some limitations whereby someone can be feeling limitations of the model. Someone can be like feeling in this way, and then they input. Someone can be feeling maybe anxiety, and then they put another condition which are actually they're not facing. So this can this input for the model, it will create the music. So and this will be targeting a different target on the brain, which will not be so good. Then the brain's reaction to music is so unique that someone cannot can be there and they don't feel like, and their culture, they are not interested in this kind of like music or notes. And then for the system, we won't be knowing. So these are some of the limitations. Yeah. And then clinical validation, because we haven't made trials, so we need to make trials and see, to make medical tests so that we see whether it's working or yeah. And then in conclusion, this model is going to be generating personalized brain targeted therapeutic music, promising for both wellness and clinical applications. So, but then we are going to make further testing to see whether it's working just as fine as we want. Then the future works going to improve personalization, including a more diverse and large data set, and also to train on more data samples such that we can be able to generate or create nice music. All these are the references. You can screenshot and then read through or make some research. And we acknowledge our supervisor, who is Dr. Galiwango Marvin, for continued guidance because it hasn't been so easy to create this model. So shout out to him. That comes the end of my presentation. Don't forget to subscribe, share, and comment. Have a nice time.